Hi, everyone. We're doing more problems on sets today. Here's the first problem. Use Venn diagrams to check whether or not the following property is true. If the property is not true, give a counterexample. So take a little bit of time to think about that, and we will then do it together. All right. Does anyone want to write down what they did?
Like annotate on the screen or just say
Yeah,
what we
sure. Mhm.
Okay. So what I did was, hold on, let me get the annotation. Okay. So what I did is I took this first part right here, the B union C, and I made sure, so that's just combining both of these sets right here. And then it says everything that's not in A. So what I did is I just got rid of these, this like, well, it's kind of hard to erase, but I just included then, or maybe if I, that just meant that we just include everything that's in B and C and not A.
Yeah.
This darker shaded part.
Yeah, that's exactly right. We just have to get rid of what's in A. I think maybe my screen is lagging a little bit behind yours.
Yeah, I just couldn't erase that like little part that's just like right here.
Let me, oh yeah, that looks good.
Yeah.
Okay, there, yeah, perfect, yep. And then how about the right-hand side?
Do you want me to do it too?
If anyone else would like to, then we can do it, but if not, go right ahead.
Okay. So for this one I did, let's see here, everything that's in B that's not included in A, so that's this section right here. And then the next part that says everything that's included in C, but not A, which is this part right here. And this statement together is saying these two combined, which would just be this whole region. Right? If I understand that correctly.
Yeah, the union just puts them together. It's all of that together. So yeah. So then what is your conclusion?
I said that the left-hand side is equal to the right-hand side.
And why is that?
Because you can see right here that this is the part I'm kind of confused about. Like, how would you like get full credit for the answer? But my reasoning is because B and C are the same shaded regions on
Yeah.
both diagrams.
Yeah, on the left-hand side and the right-hand side, the shaded regions are identical. So based on our Venn diagram approach, we would conclude the two sets are the same. So,
Sweet.
are there any questions or, thank you, Lewis. Are there any questions or concerns about the argument for this one?
I had a conceptual question.
Mhm.
So I haven't seen this done before, but if they include like let's say these were giving in set notation and they decided to include the universal set. So let's say there was just some universal set, right? So we would write the universal set here. If we were to do this operation, everything that's included in B minus A,
Mhm.
what would this operation look like? We did everything included in the universe. Or
So that's a good question. If we include a universe, then a standard just in general is that A minus B is A intersection B prime, B complement. And so this is what we would fill in. So it would, yeah, this is what it would be. So that would end up being all of A, and then in addition to everything that's not in B, which would just be all of the, or it would just be anything that's in A and is also not in B. And not B would be all of this.
okay, that makes
Yeah.
sense.
And then we're just taking the intersection, which just ends up giving us just this part. Yeah, so nothing actually changes here. So, all right, so let's do the next one. For some reason, I'm not, oh, there's the chat. Okay, I see it. Let me just put it up there. All right. Okay, the next problem is this one, where prove that A union B intersection C is a subset of A union B intersection A union C. So take a moment and think about that, and then we'll work it out. All right. So the general approach to proving a set statement like this is to show that every element on the left-hand side is so every element that is a member of the left-hand side is a member of the right-hand side. That will show that the left-hand side is a subset of the right-hand side. So that's our strategy for this problem. So to do that, I'll just write down the statement we need to prove. We need to prove this, that if X is a member of the left-hand side, then that implies that X is a member of the right-hand side. So that's what we mean by, or that this will be sufficient to show that this shows that every element that is in the left-hand side is a member of the right-hand side, and therefore that the set on the left-hand side is a subset of the set on the right-hand side. So that's the general approach. So let's take an element on the left-hand side. So this is what we want to show. So I'll just say this is what we want to show there. And so let's now take an element in the left-hand side. And does anyone want to share what they did next? What their next thought was at this stage? All right, so we know that X is in the left-hand side, and the left-hand side is A union B intersection C. So this means that X, because there's a union there, the union becomes an OR when we have an element that's in the set. So we have X is in A, or X is in B intersection C. Okay, so now we have this OR statement. And so there are three things that could really be going on. X could be in A and not in B intersection C. It could be in B intersection C and not in A, or it could be in both. But we really only need to consider two cases. One is that X is in A, and the other is that X is in B intersection C. And in both cases, we need to show that X will be in the right-hand side. So let's do the first case. And that's going to be that X is in A. Okay. So if X is in A, well, then X is in A union B. So X is in A union B. X is in A union B. So I guess you could say I'm skipping a step right now. I might really say, well, X is in A or X is in B, because X is in A, and therefore X is in A union B. So that's the reasoning. And then we have exactly the same thing going on with X being in A union C. X is in A, and therefore X is in A union C. So we also have that X is in A union C. Okay. All right. So now we have that X is in A union B and X is in A union C, and therefore X is in the right-hand side. Okay. And then the other case is that X is in B intersection C. X is in B intersection C. Okay. Okay, so what does this mean? It means that X is in B and X is in C. Okay, so if X is in B, since X is in B, that means, oh, this is a B. Since X is in B, sorry, let me make that slightly more clear. Since X is in B, X is in A union B. So that means that X is in A union B. Yeah, okay. And then since X is in C, X is in A union C. X is in C. X is in A union C. Okay, and now that we know X is in A union B and X is in A union C, X is in the intersection of A union B and A union C, and so X is in the right-hand side. So, Lewis, you have a question? What's up?
Yeah. So how did you determine the cases? Because in some problems, it's not very clear, but in this one, it was kind of clear. What's like the general approach to determine the cases?
So we have the statement that X is in A or X is in B intersection C. So that's a logical or. So just from the truth table, the logical, if we have a statement which is a logical or, it means either this is true, this could be true, or this is true, or they're both true. So in any case, one of these two statements is true. So either one case would be X is in A, but if that's not true, then definitely because of this is a logical or, X would have to be in B intersection C. So one of these two things must be true. So that's why we have these two cases.
Okay, so if it wasn't the union operation and instead it was intersect, that would be and, so there'd only be one case, right?
That's exactly right. Yep.
Okay.
Yeah. The one case would be the one case in this case, if we had replaced this intersect or this union with an intersect, the one case would be that X is in A and X is in B intersection C. In other words, X is in A and X is in B and X is in C. So, all right. Are there any other questions about this problem? Okay. So the next one, take a minute or two to think about this, and then we will do it. All right, so let's start by writing the left-hand side down, and then we'll try to apply these rules and arrive at A union B. So we start off with A union A prime intersection B. Does anybody want to tell me the first rule that they applied?
I applied distributive.
Okay, so let's do that. That sounds like a good idea. So we're using the distributive property. And that's going to give us A union A prime. intersected with A union B. All right. Does anybody want to tell me what they did next?
Negation.
Okay, so negation is right here. So that makes sense. So that means that this A union A prime is going to become the universe, the universal set. So this is negation, negation, and that's going to be U intersected with A intersection B. A union B, sorry. Okay. All right. Does anybody want to would like to say what their next move was?
Identity.
Okay, so identity is right here. Okay, so that is the right idea. I think Dr. Cohen is very committed to writing in these commutative operations or explicitly stating that we're commuting sets.
Yeah.
Yeah. So that's exactly the right idea. But first, we're just going to put in a commuting. We're going to commute these two quantities, or these two sets. So this will be A union B intersection U. And then, as Lewis mentioned, now we can apply the identity. So here, this is our A union B, and then we have the universe. So applying the identity operation, we are left with A union B, and we're done. Are there any, okay, so Mike has a question. Given that we have the original statement, could we apply absorption to try to prove that the left-hand side is A? So, okay, that's a little bit tricky. Actually, if we look at absorption here, this is a good question. The issue, it seems very tempting, but the problem is that we don't have a common term. So here, notice we have A, and then we have union A prime intersection B. We don't have A union A, or if we had A prime union A prime intersection B, then we could use absorption. But we can't use it here because these two terms are not the same. Not the same. Is that helpful, Mike? Okay. Yeah. So, but that's a good idea. You just have to make sure that the symbols match up. So, all right. Okay. So the next thing we'll do the next question now. Here it is. Okay, prove the following statement about sets. And we'll take some time to think about that. All right, so we have another one of these subset inequality, subset. We're trying to show that one set is contained in another set. So we're going to follow the same strategy that we did, the same general strategy that we did on the last problem where we tried to show that one set was contained in another set. In particular, we're going to show that if we take an element in the left-hand side, then we must show that it is an element in the right-hand side. Okay. So just to set that up, let's say X is in the left-hand side. Say X is in the left-hand side. Okay, so first let's just write out what that means. That's the first step. So what does this mean? It means there exists a integer n in Z, and there exists a integer k in Z, such that x is equal to n squared minus 1, which is also equal to 2 times k. All right, so now we want to show that x is a member of the right-hand side. That means we want to show that x is a multiple of 4, an integer multiple of 4. So does anybody have any thoughts about where they went from here? Okay, adding 1 to both sides. All right, we can try, yeah, let's, and that state that n squared is odd. Ah, okay, so you're trying to show that n squared is odd. Okay, so that's a good idea. So let's try that. So if we add 1 to both sides, as Ethan is saying, then we end up with n squared is 2k plus 1. So this means that n squared is odd. And that in turn means that n is odd, because an even times an even is an even. So n is odd. So we've just shown, so just to write this up, just to be more explicit, so n squared is odd. Thus, n is odd. N is odd. And so Ethan was thinking, well, was thinking about showing that n squared was odd and subsequently that n is odd. But you know, if you're doing this proof, you might not initially see why we would want to show that n is odd. But the reason why is because if we know that n is odd, so then we can write n, so n is equal to 2 j plus 1 for some integer j. Okay, for some integer j. All right, this is an integer. So again, what we're after, as Ethan points out here, is we're trying to show that x is an integer multiple of 4. So if we know now that n is odd, we can go back and plug in here into our equation for x, and we'll see if that helps. So we do that. So x is equal to 2j plus 1 squared minus 1. All we did was plug in for n now. And so if we distribute that, then we end up with 4j squared plus, okay, you have 2 times 2j, so that's 4j. And then you have, you add a 1 to that, and then we subtract 1. And if we just write this out with factoring out the 4, and the 1 cancels at the end there, we have 4 times j squared minus j, and j is an integer, and the integers are closed under multiplication and addition and subtraction. And so we conclude, so j squared minus j is an integer, and therefore x is an integer multiple of 4. So x is in the right-hand side. All right, so we have just shown that every element that is a member of the left-hand side is a member of the right-hand side, and therefore we've shown that the left-hand side is a subset of the right-hand side. That's a good way to do this. And if we just take a step back and we go back to right here, when we started, well, all we knew when we started was that n squared minus 1 was equal to 2k. So if you're having trouble thinking about where to go next, one thing is to just try to write down things that we know and try to use things that we know. So whenever you're trying to show that one thing implies another, what you start with, you want to know what does that give you? And in this, so if you just start writing down things that that we know, one of them happens to be that n squared is odd. That's one of the first things that you'll observe, is that n squared is odd. So you might not see how that helps you originally, and that's the point where you say, okay, well, what am I trying to show? And does n squared being odd help me show that? So that's kind of, I guess, how you might be thinking about doing this proof. Strategically. Are there any questions about this one?
So I got a little lost there for a second. Why do we introduce j? Why do we put 2j plus 1?
Because n is odd. So that means that n is 2j plus 1 for some integer j.
Oh, okay.
All right. If there's any other questions, feel free to ask at any time. So we'll go on to the next one. Rewrite the following set equalities in Boolean algebra notation. Okay. Well, give you a couple minutes to think about this one. All right. So let's start this. Before we start to write everything down, it is useful to rewrite these differences, these minuses. They're set differences. These set difference symbols. It will be useful to write them down in terms of intersections and complements, because we know how to translate intersections and complements into Boolean algebra notation. So let's just rewrite the statement. This is A intersection B intersection B intersection C complement is equal to A intersection B intersection C complement. All right. I guess we use a prime for that. Okay. So, all right. So now we're ready to do the translation. So all of our intersections, well, first of all, our sets become Boolean symbols. So A is going to become little a, and capital B is going to become little b. And then the intersection, if you remember, the intersection in Boolean algebra is this symbol, the dot. So this becomes A dot B, and then this here, so we have B intersection C, so that becomes little b dotted with little c, and then we have we had a complement, so we use the same symbol for complement that we do in set notation as we do in Boolean algebra. So this just becomes a prime, and then we still have this dot to indicate this intersection. Okay, so just the order of operations, you want to be careful. We're taking this complement first, so you might put that in parentheses and then have this outer parenthesis like that. And then on this side, A intersection B. Okay, so again, we're just replacing our intersection symbol with the dot symbol, the Boolean symbol. And then we're intersecting, so we have another dot. And this is going to be with C prime, so this becomes little c prime, and to indicate the order of operations, we might put a parenthesis around this and then another one around the whole thing to indicate that we're doing the complement of C before we do the multiplication, the Boolean dot. So I know that was a little quick. I'm just trying to get through this one so we can look at least one more. So given that was fast, if you have any questions, you can just type them in the chat right now, or we can discuss it if you feel comfortable asking out loud. I'll wait for like 45 seconds. Oh, so Mike has a good question. Actually, we're not trying to show a set equality here. We're actually just trying to rewrite the expression in terms of Boolean algebra. So we're actually not trying to prove anything. In this question, we're just getting practice writing out the Boolean algebraic equivalent expressions of set equations. So there's nothing, you could prove this statement if you would like. That would be nice, good practice with manipulating sets and proving set equations. But here we're not focused on that. All right. So here's the next one. So we do want to prove something. We're not just translating from one notation to another. We want to prove that we're using Boolean algebra. If AB is equal to A, then A prime plus B is equal to 1. So take a minute or two, and then we'll do it. Okay, so we want to show that this equality holds, and we know that this is true. So let's try to use what we know. So the way to do that is this. We're starting off with A prime plus B. We want to show that it's equal to 1. We know that A is equal to AB. We want to use what we know. We want to use our assumptions. That's something we should be thinking about. So let's use the assumption that A is equal to AB. So then we plug in for A, AB. All right, we're trying to get 1. That's what we want this to simplify to. Does anybody have in mind what the next simplification might be? What rule they would use to simplify this expression next? Yes, De Morgan's rule. That's a great idea. So we have this AB prime. So we're going to apply De Morgan. So this is going to become, using our Boolean algebra notation, this is going to be A prime union B prime plus B. Sorry, not a union. So in Boolean algebra, the union becomes a plus. So it's easy to get confused. So let me erase that. So that's plus B prime plus the B. Okay. So the next one, oh yeah, so we would say that this is De Morgan. We use De Morgan. The next one, so Dr. Cohen would like us to be explicit with everything we write down, so we're going to apply the associative property next. So the associative property is going to let us write this as A plus B prime plus B. Okay. So just to rehash where we were at, we applied De Morgan, which was AB prime. That became A prime plus B prime. So in reality, we have these parentheses around A prime plus B prime because that's what this became. And then we're adding B, and now we're using the associative rule, associate. Okay, and then, well, what are we going to do with B prime plus B? Does anyone have any idea what to do with B prime plus B? Yep, that's right. So negation is right here. So B prime, okay, so technically, according to the practice that we want to use in this class, negation is the right idea, but we first need to use the commutative property. So we're going to flip the terms just because we have a B prime plus B and it should be a B plus B prime. So yeah, it's a little bit annoying, but we've got to do it. So this is B plus B prime. And then as Mike points out, now we can apply negation. So when we apply negation, the B plus B prime becomes the universe, which is 1 in our Boolean algebra. So this is now A prime plus 1. And then we're almost there. So does anybody, again, we want to get 1. That's what we're after. So what's the next simplification that we need to make?
Don't we want to use the identity? Because isn't the 1 the universe set?
Let's see. So the issue.
Oh, wait,
Not
no.
quite.
Yeah.
Yeah. So I'm not. Oh, here it is. It's the universal bound. So the U is a 1, and the A prime. This plus is a union. That's a union. The 1 is the universe, and the A prime is back in our set notation. That would be in like an A prime. So now we're taking a set union with the universe. So that's the universal bound. So that's just going to be the universe, which is 1. So we're done. Are there any questions about this one?
So when we switch to Boolean algebra, oh wait, never mind. I see what you did. Never mind. I just answered my own question.
Okay. So let's see here. What remains, which we didn't get to, was only one problem. So actually, I think this one is on the homework as well. So these discussion slides are posted, but of course this problem's already online. It's 3:45. So that's it for today. Note that James has office hours at 2 p.m. So if you have any questions about the material from the day, make sure that you head to James' office hours.
Oh, and then those were swapped. We sent out an announcement and stuff.
Okay.
So their office hours are from 5 to 7 today instead with Nancy.
Okay. All right. Thank you. Sorry about that. Sorry for.
Oh, you're good.
All right. I'm going to stop the recording now.